Okay, so Pooria Madani is going to present his work on MAC layer spoofing and detection, and he's discussing randomized moving target approaches. So please get started. Thank you.
All right. Thank you very much. My name is Pooria, and I will be speaking today about some robustness in statistical and machine learning-based methods that are used for MAC layer spoofing detection, how an adversary could potentially evade the state of the art, and we're introducing some sort of a randomization mechanism on top of the existing models in order to introduce some degree of robustness against potential adversarial evasion attacks, which all of that are subsequently going to define in this presentation. So my talk is divided mainly into two segments. One is the current state of the art spoofing detection using a very specific non-cryptographic but a specific feature, and how adversarial could potentially evade detection. What's the doability of that? And then I'm going to introduce a randomization schema that could treat any sort of a detection mechanism as a black box, just introduce some degree of randomization to attain a desired level of robustness, which I'm going to show some experimental results and some point of discussions. So it doesn't need a lot of convincing, especially for this audience, that MAC addresses are used in different configuration and settings for different purposes, mainly for identification of nodes, but they've heavily used in many classification and many protocol algorithms. An adversary could, in some context, some specific context, by spoofing that, gain certain advantages. And because of that fact, the idea of MAC address spoofing detection become prominent and important. And of course, that given the with the IoT, that there are a lot of wireless communications happening, and the devices, they don't have necessarily a human identity, but an actual hardware identity, that MAC address spoofing can play an important role. That needs to be studied further again for specifically for IoT applications. Well, of course, we all know that from our history that we've got some potential defenses using cryptographic authentication protocols that we say that we don't necessarily just take it on the face value that someone claims that owns a MAC address, but we're gonna ask them to provide some sort of a proof to that, such as public-private keys, or provide proofing through some sort of a secret computation. There are other studies that have studied the idea of using channel and signal signatures to establish some sort of an identity for participating devices. And the main argument for that is many of IoT devices and wireless sensor networks nodes, they are not they don't have resources that it takes to most of the times to carry out some of the cryptographic authentication protocols to do encryptions. They could be resource intensive. And there are certain challenges with cryptographic protocols, such as key distribution. Might as well, just to have an added extra layer of security, we go after signal and channel signatures in order to do the identity profiling, and just don't rely necessarily on the cryptographic authentication, because they potentially face computation resources or other form of challenges, such as non-expert home users. For example, it was published that flip hue smart bulbs, they forego of using authentication, proper key distribution authentication protocols, because they were targeting home users, and they wanted the home users to have the luxury just to put the bulbs in and work. They don't necessarily need to understand the pairing and so forth. So these are the actual limitations of cryptographic defenses, which opens the door to study other form of signature and profiling for the identity. And the other thing that I wanna mention, that for most of the cryptographic systems, authentication protocols, we assume some degree of physical security. In most of the IoT, that's not necessarily the case. There are sensors that are deployed in wide area networks that are accessible by the adversary, and doesn't matter if you've necessarily got a cryptographic key inside those devices, and if those devices get stolen, the adversary could potentially extract that very authentication key that you have installed. So the idea is, let's use these signals as another means of authentication, because these signals are affected by many environmental variables, such as obstacle, distance, transmission power variability, antennas using devices, that is kind of hard to be replicated by an adversary that is trying to take over on the identity of a player in the network. And they are sort of act as a random variables. The variables that we could model them using many statistical and learning algorithms. And let's define a model to verify that identity. And we're gonna go from a physical environment measure to establish some sort of an identity for our participating nodes, and use that to detect if a MAC address that is claiming to has an identity, it's been taken over or not, because we are assuming that's kind of harder to spoof. It's harder to spoof the obstacles, it's harder to spoof the distance and so forth. So of course, the general idea behind such RSSI-based receive signal strength indicator-based kind of an authentication is of two phases. The first phase is the training phase, where we are assuming that the participating nodes are stationary, and that's not my assumption. This is the state of the art assumption by the community, that the receiving node will profile the sending node by forming the collecting some samples, forming the RSSI distribution, and at the runtime, they're gonna collect again the RSSI values, and they compare the collected sample with the training sample, such as, for example, likelihood ratio tests, to see if there's a substantial deviation from that profile. It's a form of anomaly detection, if you will. Well, but here's how a potential adversary could evade the detection, just to give you a perspective of that. So in the training phase, the legitimate sender will establish some sort of a legitimate profile with the receiver. For example, that could be a normal distribution of RSSI value that the receiver forms and records as a profile of a legitimate sender. Then the adversary comes into play, and they try to establish takeover on the legitimate sender identity. But of course, the transmission that they make, the RSSI distribution that forms by the receiver, it's totally different. And it is the goal of the adversary, for the purpose of evasion, smartly to adjust its transmission power so that the form distribution on the receiving end matches the same profile of the sender. Historically, it was believed that such manipulation of transmission power is not really doable, is not given the obstacles, is not necessarily a doable thing. But it turns out, with all these off-the-shelves software-defined radios, this is an actual doable activity. So the adversarial goal is to evade detection by adjusting its transmission power in order to cause the same distribution to form at the receiving end, that it does the anomaly detection. And the adversarial strategy is extremely simple: is listen to the network, using the signal strength models that we have, find the approximate locations as a mental picture of the receiving and the sending node, and then after doing that trilateration, figure out a range of power, transmission power, that you gotta use in order to make the same distribution occur at the receiving node, and then search through that range of transmission power. Try different transmission power to see which one allows you to pass through, assuming that there is some sort of a feedback mechanism by the receiver when it's received the legitimate packets. In our previous work, we developed a theoretical multi-arm bandit search where, given a range, the adversary, instead of brute forcingly search through this range, they compute as some sort of a mental picture of what is doable and what's the probability of evasion in that search space, and the adversary iteratively it can mathematically encode its uncertainty as well, which is demonstrated in this picture. For example, the adversary, after doing the initial computation, they know, for example, that they can use at least two range value in the range of transmission power to evade detection, but not necessarily with 100% probability because of all those environmental factors. And they can encode their uncertainty as well using a Gaussian regression process. And the idea of this is to iteratively try to reduce the uncertainty of the probability of evasion. And the adversary in each iteration picks out a point that is uncertain about a transmission power, and they query and see if they can evade detection using that particular transmission power, and they record the probability of its evasion, how many of those packets got passed through, how many got blocked, and that would be the probability of that trial. And iteratively, the adversary does so until it finds a transmission power that evades detection by a desired probability, and it has reduced its uncertainty about the belief. So that's a query strategy, and we demonstrated that it doesn't take long for an adversary to do that. It doesn't need to do it brute force. They can use this method as a form of a multi-arm bandit search. So it's a doable thing. So it doesn't matter what kind of a detection model that you have at the other end. Using this method, it only takes polynomial mini query for the adversary to evade detection. Now, here's come the idea of our randomization. And we said that, okay, if this is doable, that's a bad news for the community. So it doesn't matter how smart you are about your modeling techniques if the adversary could evade it using polynomial mini queries. Let's randomize that. That's the only logical way around it, because the adversary is using the feedback provided by your architecture to form its belief, try to reduce its uncertainty. Let's introduce some randomness in order to increase that uncertainty and make the adversary to incur some losses. So the idea of a randomization is divided into two parts. The first is to create some encompassing intervals, especially for the received signal strength, because it has a Gaussian-like distribution. And in most of the literature, they use mixture models, mixture of Gaussians. It made sense for us to create intervals that are encompassing. And based on the, we created this formula for interval creation. The system operators chooses how many number of the intervals that it wants and what is the spacing of those intervals. The spacing could linearly get expanded and covers more, or it could covers not necessarily a linear using the R parameter. And that would be the number of the intervals essentially would be the number of the models that we would like to use at the runtime. So instead of just having one authentication model, we're going to be training one authentication model using the data that falls in one interval. And at the runtime, we're going to select one at random each time in order to handle the query. So you can imagine that if the first interval, for example, selected randomly, there's going to be some false positives, but that false positive is also a cost on the adversary as well in terms of the belief that is developed. And now comes the second idea, that how do we go about selecting those intervals. And we propose the use of a beta binomial distribution because the parameters that the beta binomial distribution that it gives us, it allows a system operator to emulate any form of a discrete distribution that they like. Do they like to have a uniform distribution to selection among those that? All right. So now the idea behind the randomization schema is to divide and make it made up of certain number of intervals, and the basic idea is instead of just training one model, we're gonna use the training data that falls within each interval to train a detection model on its own. And at the runtime, we're gonna select randomly among those models. And of course, the models that have a narrower set of training data, they are more aggressive because they're prone to more false positive. They're stricter. They are forming around the mean versus the intervals that are larger. They have more training data to them. They're more lenient to accepting traffic. And because of these random selection among them, it is hard for the adversary to know exactly the model, the belief network that is forming, its uncertainty. It's about which of these models, because the adversary doesn't know how many intervals there are and how aggressive each interval is or how they are even selected. So they have to do extra queries to even understand about this idea of randomness. And the main idea is, because of that extra queries, there is a more chance for the other defense mechanisms to kick into place and find a mischief is going. And our way of formulation of creation of interval, the system operators giving an n, which is a number of the intervals, and r, which is the spacing of the intervals, and that falls on the system operator's discretion. The second main question is, now we know the system operators select a certain number of intervals and how big they should be. How do we go about selecting them? And we choose to do that selection through a beta binomial distribution model, because through alpha and beta parameters, the system operator can choose any form of distribution that they desire. That could be a uniform distribution, or it could be Gaussian-like distribution. They have the control over the form of the selection that they desire. And of course, this random selection based on the parameters of alpha beta, they result in a different cost profile, a false negative and false positive. And given that in different contexts, we could have different costs associated with false positive and false negative, this would be a parameter optimization of the system operator. Given their cost and their risk profile, do they want to allow more false positive or do they want to allow more false negative? And which alpha beta combinations will give them the best risk profile that they desire? So given this randomization schema that we've introduced, we selected a state-of-the-art detection RSSI-based detection model from the literature, and we launched our multi-arm bandit-like attack against it. And we saw that if you don't use any sort of a randomization in the orange graph, the adversary can find transmission power that can evade detection with any level of accuracy that the adversary desires. 100% evasion detection, or that also, if the adversary uses if the defense mechanism uses a randomization framework, and we still launch the multi-arm bandit attack against it, we are introducing a lot of uncertainty, and we decrease the probability of evasion by order of magnitude significantly. The other observation in our end was, doesn't matter what level of desired evasion of probability in the adversary, they can, using constant number of queries, they can evade detection, find a transmission power that can evade detection at any level of the desired evasion probability. But if you introduce this randomization idea, the adversary, they have to issue order of magnitude more queries in order to evade detection, find a transmission power that can evade detection with certainty. And that increase of number of queries, essentially that means translate to increase more network traffic, and hopefully there are other mechanisms in the network that can detect such spikes and that can trigger other set of alarms as well. Of course, as for the conclusion, the idea of randomization always comes with a cost. We already established this idea that the randomization create the extra false positive or false negative cost, and that's the cost we have to pay when we are using some such statistical models. But does this needs to be a full-time system, or can it become some sort of a part-time system, meaning that we have a more of a triggering part first that identify that there's going to be a discovery attack going on. Let's activate the randomized detection mechanism in place, or does it always have to be on, and we have to take some sort of a cost-sensitive study into account when we're setting our parameters? The other idea is, and that's not necessarily about our work, it is about the state-of-art RSSI-based spoofing detections. That what happens if both the transmission, the attacker, and a legitimate node, they start to transmit together simultaneously. Given that most of the RSSI-based spoofing detections, they take into account some sort of a windowing mechanism of collecting some RSSI values together first before they do detection. What happens? Some can argue that, for example, in wireless sensor networks, you've got a sensor that is deactivated for most of the time. They just come online for a very short period of time. They transmit their readings and they go back to sleep. So we don't need to worry about that. But given other settings of IoTs, that assumption could not necessarily be true. And should we consider that in our randomization mechanism? Can we make use of that fact to create a more part-time randomization idea? So sorry, I do apologize for the hiccups, at least on my end, for loss of internet connection. This would conclude my presentation, and I can take questions if there are any.
Thank you very much. Let me just pause the record, stop the recording.